Three, two, one. Time for another 2070 online section video. Alright. Okay, so today we're going to talk about something pretty cool. We're going to talk about the dimension of a vector space. Okay, and what is the dimension of a vector space? Well, plain and easy, it's the number of elements in a basis. Alright, the end. Video's over. Well, obviously not, because hopefully a question immediately jumps out at you. In order for that to be well defined, it's got to be that any bases have the same number of elements, because otherwise, right, if there was a basis that had 3 elements and a basis that had 7, well, then what's the dimension, 3 or 7? Right? So, obviously, given any two bases, they probably have the same number of elements. That seems pretty reasonable. Otherwise, we wouldn't be talking about the dimension of a vector space. But let's ask the annoying question: why is this true? Okay, and it turns out to be pretty straightforward to justify why this is true, and actually we'll establish a pretty important fact regarding essentially how linearly independent things have to behave. So suppose we got a vector space and a basis, and let's say we got a list of elements that exceed the number of elements in the basis. Okay, well, for each one of those elements v1 to vm, we know we can create the coordinate vectors for them, as we discussed previously. But now you have a list of m things, and they live in Rn, and as we know, if you have more vectors in Euclidean space than you do the size of the Euclidean space, then we know that they are linearly dependent. So I can find scalars to make the trivial linear combo, and at least one of the scalars is non-zero. Now, the coordinate mapping is linear, so this linear combo can be reconstituted as follows. So note, when we talk about linear mappings, we talk about mappings that could take a linear combo and turn them into another, but you can go backwards. And another fact about the coordinate mapping, as we discussed, is that it's an isomorphism, meaning that if this is getting mapped to 0, the only thing this could be is the 0 element of the vector space, and there we have it, v1 to vm must be a linearly dependent list, right? So note, basically, we just took something we already knew in Rn. If you have m vectors and m is bigger than n in Rn, we know they're linearly dependent, because if you set up the augmented matrix, you're going to find that there is free variables, and thus there are non-zero solutions that can be found. And now we see that we can kind of carry that back over the bases. Carry that over the generic vector spaces. Alright, now equipped with this, let's establish that any two bases in a vector space have to have the same number of elements. So let's say we have two bases with a list from b1 and bn to a list from h1 to hm. If n is less than m, then this must be dependent, but that contradicts that it's a basis. And likewise, if m is less than n, then this is forced to be dependent, which again will be contradictory. Therefore, n and m have to be equal. So, given a vector space, we can officially write dim of the vector space to indicate the number of elements in the basis. Okay, now, before moving on, let's talk about something. We, in this class, are only going to care about the situation where the basis has a finite number of elements. Okay, now, it's worth noting that for the infinite dimensional case, dimension can still be defined, but it kind of loses a little bit of its meaning, because once you've gone infinite, things get a little weird, because when you say same number of elements, what you mean is that there is a one-to-one and onto mapping between the sets. And it turns out that if that's your definition of how many things you have, you can get more than one infinity, and the waters get murky very quickly. So while you can go infinite dimensional, and the branch of math that cares about infinite dimensional vector spaces is called functional analysis, it's possible, but for our more algebraically focused methods here in the class, we're only going to worry about the finite case. And speaking of which, now that we have an official notation for dimension, we can go to a good vector space, like the polynomials with degree less than or equal to 3, and note that it is 4-dimensional, because 1t, t squared, and t cubed forms a basis. Alright. Now, before we go any further, let's make some quick notes that are going to help us out here. So, obviously, we have our usual Rn, or our polynomial spaces, that are finite dimensional and have dimension 1, 2, 3, and so on. But it is possible to be zero-dimensional. As we've mentioned, the vector space consisting of just the additive identity counts as a vector space. It is trivial, and so we will give it dimension 0. Because if you look at how linear independence and span are defined, we did it for finite lists. It turns out you can extrapolate it to any subset, and thus you can then apply that to the empty set, and it turns out the empty set ends up being technically a basis. So the trivial vector space, will count that as zero-dimensional. Keep that in mind. All right. Another thing that's worth mentioning is that if you have a subspace of vector space, the subspace's dimension obviously does not exceed the dimension of the original. And the only way that the dimension of the original matches the dimension of the full space is if the subspace and the vector space have the same dimension, or are the same set. And that can be easily seen by noting that if H was a proper subset of V, well, then there's room to find more linearly independent things, and thus the dimensions would not be equal. Okay. While we're here and talking dimension, let's look at a fun example. Here's a sizable matrix, a 4 by 5. Right. So the ref of the matrix is as follows. So we have a 4 by 5, and if you compute the ref, it's this. All right. Now, given a matrix like this, once we've computed the refs, hopefully a couple things immediately stick out to us, because as we recall, when you're looking at matrices, one of the things you're interested in are its null space and its column space, and the ref will allow us to find such things. All right, so first let's talk about the null space. So if this is what we're looking with, then we know that on the element x in the null space will satisfy the following list of equations. That's coming from here. Okay, and then from here we can see that x2 and x4, because note x2 and x4 are the non-pivot columns, we can use those to get a basis for the null space, because then we can find that any element of the null space will depend on what x2 and x4 are doing, and you can clean it all up and pull it apart like this. And this set right here, these two elements of R5, will form a basis for the null space. And hey, look, there are two things, so I can tell you the dimension of my null space is 2. All right. Now, furthermore, we know then that the first, third, and fifth columns are the pivot columns, and so then we can pick those out of the original matrix, and that gives us a basis for the column space. And note, the dimension of the column space here is 3. The dimension of the column space plus the dimension of the null space is equal to 5, which just so happens to equal the number of columns. All right, so let's point out that was not a accident. That always happens. But why? So take an m by m matrix A. The dimension of its column space is called the rank of the matrix, which we denote as rank of A, like that. And as we've seen, the basis for the column space is found by identifying the pivot columns. So the rank is the number of pivot columns. All right. Now, similarly, a basis for the null space, as we pointed out, is found by identifying the free variables, which are the columns that aren't pivot columns. So the dimension of your null space, which is also called the nullity, has to be the number of columns that are not pivot columns. All right, so if you add up the rank and the dimension of the null space, that's the number of pivot columns plus the number of things that are not pivot columns. By the good old law of excluded middle, that means we've got every possible column, and there we go, the rank theorem, or the rank nullity theorem. One of my favorites. This is such a neat little result to me. It's quite beautiful. And what's really beautiful about it is that I get to ask all sorts of obnoxious questions of you now. Okay, so let's say you've got a 3 by 8 matrix and you know its rank is 3. Well, the rank theorem then tells us that 3 plus the dimension of the null space is 8, which forces the null space of dimension of 5. So I already know something about the null space, and all I had to do was compute the rank of the matrix. And vice versa. Let's say you've got a 6x5 matrix whose null space is 4-dimensional. All right. Well, the rank theorem then tells us that rank plus 4 has to equal the number of columns, which is 5, and so the rank has to be 1. Right, so if you know the rank, you immediately know the dimension of the null space, and if you know the dimension of the null space, you already know the rank. All right, those are too easy. Here's a more fun question. Let's say I gave you a 6x8 matrix. What's the smallest possible dimension of its null space? Ooh. All right, now we got a question. So let's note again, the rank theorem tells us that the rank plus the dimension of the null space is 8. Now, if I want the smallest possible dimension of the null space, that means I need to make the rank as big as I possibly can. And we were told something. So note, so far in the previous two examples, this 3 and that 6 did not mean anything. It had no consequence on any of these questions I was asking. But now it matters. Because there's only 6 rows, that means we know that you can have at most 6 pivot columns. Right, the non-zero rows would correspond to the pivot columns in the ref of the matrix. So that means you have at most 6 pivot columns. It means your rank can be at most 6. That's the largest possible rank. And if you plug that in, you can then find that the null space's smallest possible dimension is 2. So in other words, the dimension of your null space has to at least be 2, if not more. Because it's very possible you do not have 6 pivot columns, you could have less. So here we see this matrix, the size of this matrix immediately forces the null space to have stuff in it. Which, again, we already know that information, right? I have more columns than I have rows, which means I have more variables than I have equations. Right, so that lines up with our intuition. That's why the rank nullity theorem is sometimes referred to as the fundamental theorem of linear algebra, because it basically captures that intuition of, if I want to solve a system of n equations, I need, if I want to solve an equation as n unknowns, I need n equations. Right, I need the same number of equations as I do unknowns in order to solve. If I have more unknowns than equations, well then there's some variability, and if I have more equations than I have knowns, well it's possible I've got too much information and I'm not going to be able to solve things. So, beautiful, pretty cool. Nice theorem, and wonderful thing involving dimension. Alright. With that said, I'll see you in the next video.